Let's wrap up our talk on binary search trees by talking about the time complexity of the various operations. But before doing that, we'll look at a couple of example binary search trees to give us some intuition about what we might expect for time complexity. Okay, to get some intuition about how this is going to behave, let's go through a sequence of insert operations. So I'm going to go ahead and build my tree. So first off, I'm going to insert an 8. And then a 4 comes before 8, so that'll be to the left of the 8, so we'll insert that. And then a 12 comes after the 8, so that'll be to its right, so we'll go ahead and insert that. Next up, we have a 2, so that's before the 8, before the 4, so over here. And then after that, we have a 1 before the 8, before the 4, before the 2. It's the 1. Next, we're going to insert a 3, so that comes before the 8, before the 4. But after the 2, so like that. Next up, we've got a 10, so that comes after the 8, but before the 12. Next is a 6, that comes before the 8, but after the 4. Followed by a 7, which would come after the 6. And then a 5 that would come before the 6. So those last couple of steps, I took some shortcuts. I didn't talk about the full process of iterating through the tree from the root, but I am always kind of thinking through the same set of steps. Okay, so at this point we have the 11, so this time I'll talk all the way through it. 11 comes after 8, but before 12, but after 10, so it would be to the right of 10. And then 9 after 8, before 12, before 10. And then the 14 after the 8, after the 12. And then the 15 is after the 8, after the 12, and after the 14. And then the 13 is after the 8, after the 12, but before the 14. And there we go. Okay, so this should be a familiar shape. This is a complete binary tree. So we saw this when we were talking about heaps. So if we think about our operations, the min operation would start at the root and go left, left, left until it gets to the 1. The max would start at the root and go right, right, right until it gets to the 15. Any sort of insert or remove, the maximum distance it has to travel is, in this case, 1, 2, 3 nodes, essentially the height of the tree. Okay, let's move on and look at another example. Okay, let's do one more example. So in this case, we'll start off by inserting a 1. And then we'll insert a 2, which belongs to the right of the 1. And then we'll insert a 3, so that's after 1, after 2, so it's the right of the 2. And you probably see where this is going. So basically, each node here so far has nothing on its left subtree, and the nodes continually are being added to the right subtree. Okay, so the overall height of this is actually dependent on the number of nodes, the n. And essentially, this is basically just like a linked list. It's almost like we're ignoring the left subtree link altogether, and we could kind of think of the right subtree link as being our next pointer, and the root link as being the same as the left for a linked list. So this is kind of the degenerate case of a binary search tree, which is a linked list. Okay, one more example. So this time we'll start off by inserting a 1. Then we'll insert a 15, which belongs on the right of the 1. Then a 2, which is after the 1 but before the 15. And then a 14, which is after the 1 but before the 15, but after the 2. And then a 3, which is after the 1 before the 15, after the 2 before the 14. and then a 13, and you can probably see where this is going. So our previous example, that's not the only type of thing that can lead to this scenario where your tree has a lot of height, where it's kind of scraggly, it's not very dense. So again, in this case, we have h is going to be equal to n, the number of nodes in our tree. So some observations about the height versus the number of nodes. So in our best case, we basically had the complete binary tree shape that we encountered when we were working with heaps, where the height is essentially log n. But the worst case was our scraggly trees, where we essentially had kind of a linked list, and the height was on the order of n. So in an earlier part of this module, I mentioned that the array mapping that we used with priority queues didn't really work very well here. And part of the reason is because it has to have an array big enough to hold all possible nodes for a dense tree. And if we've got one of these really scraggly, sparse trees, then there would be a lot of unused, wasted space. So one way to think about that would be to think about the array index needed for one of these nodes in one of our trees, like the tree that leans really, really, really far to the right. So for this particular tree, if you remember, we can kind of compute the index of each node by multiplying the predecessor's index by 2. So if we imagine that the root node is at index 1, then its right child would be at index 2, and its right child would be at index 4, and its right child would be at index 8, and its right child would be at index 16. And you can see that it essentially would have to have an array that could contain 16 values, even though we only had 5 values being stored. So we would actually end up having exponential growth in our memory, potentially, for these scraggly trees. Okay, so some other observations. Let's do a quick review of the operations for the binary search tree and their overall time complexity. So insert has to travel up and down the tree. It's dependent on the height. Remove has to find an item by traveling up and down the tree. It's dependent on the height. The contains operation has to find an item dependent on the height. I think you see the pattern here, the min and the max. All the operations really depend on the height of a tree. In fact, it's not true of just these operations. Even our operations to find the predecessor of a node and the successor of a node depend on the height of the tree. Okay, and as we've already shown, the height is order n. Okay, so just to kind of put it all together here, since the height could be order n, every single one of our operations could be order n in the worst case, in these degenerate trees. Okay, so was all of this exercise a waste of time? No, it wasn't. So we have a great observation here that log n behavior is possible if we can somehow control the height of our tree and ensure that it's log n. So that will be the focus of our next module, and part of the studio you'll work towards augmenting trees to keep track of additional details so we can try and ensure that the tree's height is log n. So our next topic is AVL trees, where in addition to the order property, we are going to go ahead and add in some restrictions on the growth of the tree, on how we add nodes, which will essentially control its shape. So just like with priority queues, we're going to end up with kind of two sets of rules, one that dictates the shape of the tree and consequently its height, and the other that dictates the order of the tree.